Is the screen visible?
Yes,
Yes,
sir.
sir.
Okay, good. So today we will be talking mostly about two contrasting techniques in machine learning. That one is dimensionality reduction and one is transformation of a different higher dimensional space in order to apply the linear separation, all the algorithms that we learn. So both has certain insights why we do that. So we will start one by one. So first, to start with, we look at the problem of dimensionality reduction. Usually what happens, if you remember all the algorithms that you already read in machine learning, be it clustering. So when you try to make into different clusters, you need to compute distance. So if you go by Euclidean distance or any other distance format, the number of attributes or the dimension of the problem is obviously a computational issue that you face. For example, suppose you are trying to say whether a credit card is fraud or not. So you have attributes like age, salary, date of birth, and so on. And you want to say that this approval of credit card is yes or no. So this kind of classification. So the number of attribute that grows, more difficult we get to have this classifications, because each attribute is one dimension that you increase. You can think of it's a one parameter increase, and hence your VC dimension space is also becomes more fluid in that case, and so your job is much more difficult. Be it in supervised learning, be it in unsupervised learning, the dimensionality plays a role in order to make the problem computationally worse. So the computational efficiency of whatever algorithm that you give is dependent on what dimension you are looking for. And sometimes there are so many attributes to tackle that often the space in which we search and find out the solution in terms of a classification or even clustering is infeasible. And in that case, we resort to some concept which is called as dimensionality reduction. So the primary motivation of this is that not all the attributes are totally dependent to make a decision. So can we select from the set of attributes we have, A1, A2, D number of attributes? Can we select from this a subset of our attributes, AK1, AK2, AKM? Obviously, this each of these Ki is less than equal to D, less than equal to 1, and my M is less than D because I want to reduce the dimensionality and maybe more greater than equal to 1. So this is the formal problem statement we pose, that can we reduce the dimension so that I can work out the same problem, classification or clustering, whatever, in a this smaller dimension in order to reduce my computational, in order to make my algorithm more computationally efficient. So as you can see, if I draw a particular two attribute problem to visualize, suppose this is x1, this is x2, and suppose I have, let us take an example of clustering problem. I want to cluster data like this. Now you can see here that though x1 and x2, each data point corresponds to some value of x1 and x2 pair, however, in order to consider these two set of points as two different clusters, both dimensions will not matter. In other words, if we project all these points into one of the dimensions, I get a cluster of projection in that particular axis. Also, I can project all the other points into this part, and I get a cluster of points in that particular way. So the thing that we are doing is, mathematically we call it as projection into one axis. And in that case, if they are separable, then I can easily say this is my class 1 and this is my class 2. However, the important point to note is that which set of attribute I choose to project. For example, I could have also projected here. Then my class 1 would look like this, whereas I could have projected this one here. Then my class 2 would be here. Now you see the difficulty of projecting to x2 rather than to x1, because in this case, the classes that I want to get in, or even if you can think of this problem as a plus and minus, that is a binary classification problem, even in that case also, I cannot differentiate this, whereas this can be differentiated by a linear line. I cannot differentiate this by a linear line. So therefore, I can easily see from this figure that obviously projecting to x1 is much better than projecting to x2. So therefore, I need two things to define here formally. Whatever we are talking informally, two things we should define. What is projection, number one, and what is good projection or good selection of attributes, right? Because if I select x2 as my project unit, then my the separability becomes bad. So let us define these terms one by one. First, I would like to define something by which I can evaluate my projection. So how do I evaluate whether this is good or this is good? So what is we call as class separability? Let us first
Sir,
define. Yeah.
sir, the M can also be D, right, in that inequality?
Yes. In that inequality, no. I'm saying reduction. So it's I would like to reduce at least by one. So I
Okay.
put a less than. That's it. So first of all, I mean, whatever I do and project, I need to make sure that my classes are separable. So by separability, so I need to follow certain kind of evaluation index that makes me separable. And usually people follow something called KL divergence, which is invented by the scientist Kullback and Libler. Many of you have already heard this term, that it is called KL divergence. So what it does for making KL divergence to run, what it does, suppose this points in one of the part follows a probability distribution Px. These points follows a probability, another probability, suppose this is P1x and this point follows a probability distribution P2x. Remember, x is a vector because it's a pair of x1, x2 in this case, in this example. It could be a vector of d dimension. So for these two probability distributions, KL divergence formula is given as, if two set of points are drawn from these two probability distribution, we give summation of all the examples, excess of all the training examples. I have P1x into log of P1x by P2x plus again over all the examples P2x into log of P2x by P1x. This is a seminal work by Kullback and Lilber, that they provide that two distributions can be evaluated in terms of separability by this KL divergence, and they call this as a log likelihood. P1 by P2 is the likelihood, and this they mention as a log likelihood. So depending on this divergence, they found that how much divergent these two classes are if I project into some in any of the part of it, any of the subset in the attributes. So this is how we will evaluate, number one. Number two is the projection part. So if you look at the definition of projection, I will try to do it in this, I will try to think it in this way. I will try to select an attribute subset selection, right? Because projection is nothing but all possible attributes, among them the subsets that you can choose, you only project to that dimension. Suppose these were three-dimensional points, If I choose two of them, then I just project a three-dimensional point into a plane. That's it. In 2 dimensions, I project a two-dimensional point into a line. So therefore, its projection is nothing but just to select a set of attributes in order to make that point visible on those attribute hyperplane. So depending on this, we will try to develop certain algorithms of attributes selection. So as you can see, the complexity of such kind of a selection is, suppose you have D attributes and you need to select small d if you want to select it. So how many possible ways you can do it? It's capital D combination D, right? These many number of options. So it is obviously, you can easily understand this is of the order of, right? So the main problem is this many number of times I need to invoke this in order to know which of the subset of attributes is good, which is very heavy computation. So rather we will go by heuristics, and that heuristics we call it as a feature selection heuristics. So we will try to do it in two ways. One, we will try to do a forward search to find the set of attributes, and one we try to do a backward search. So let me repeat what we are trying to do. We have D attributes, I want to reduce it to small d attributes. Therefore, I need to choose a subset of it for where I get a better evaluation or the separability index in terms of, let's say, in terms of KL divergence. You could use any other parameters, but we most commonly KL divergence is used. Now, it's obviously a search problem, first of all, because for D dimensions, there could be 2 to the power D number of possible subsets, among which I am only trying to search for D subsets where this gets minimized, KL divergence gets minimized. So it's obviously it's a search problem. You can easily see it's a search problem. From D dimension, among all possible subsets, those subsets containing D elements want to minimize this KL divergence. It's a search problem, or also you can visualize it's as an optimization problems in other direction as well. So the way we will go with it is, let's say first we try with the forward search heuristics. So see, since this is infeasible to compute all of them, I will go by heuristics, which might give me a local minima, but still there is a good chance that I could get a good subset of attributes. What I will do, first I will try to select among all of these attributes from x1 to xd, which one of them, if I select, suppose I select any one of them as my subset, what is the best one attribute that I can select depending on KL divergence? One attribute. What is the best one? Then if I have got the best one, obviously x1 will provide, if I project into x1 line, it will give certain kind of divergence value. If I project only into x2 line, it will give certain divergence value up to xd. Among that, which gives me best divergence or best class separability, I will choose that. Then I move on. Then among, let's say, for the time being, let's say x4 gives me the best possibility. So now I will try to see whether x4 and x1 is better, or x4 and x2 is better, or x4 and x3 is better, so on up to x4 and xd is better. Which of them gives me better KL divergence separability in terms of the better class separability in terms of KL divergence? So here you see, one by one, I am trying to go forward and try to incorporate one by one attribute and try to select whichever is the best. Let's say this becomes the best. So let's say this is the best one that I can do. Then again I move on and try to figure out x4 and x2, which is the third component of attribute that I can do. In this way, up to I get d number of attributes being selected. Can you tell me what is the number of this computation is done here? Earlier, if I just go by DCD number of attribute selection, and every time I call it, it's order of d to the power d number of KL divergence calling I need to make. Here, how many number of KL divergence calling?
Small d to the power small d.
D square.
To the power?
No, small d to the power small d.
No, why to the power? Because see, at the first iteration, you are doing KL divergence for d number of points. At the second iteration,
Yes.
you are again doing it for d number of points. At the third iteration, you are again doing it for d number of points, up to you are doing this for
A small d
times.
number of times.
Yes. So therefore, this is d into small d number of computations.
Yes, yes.
However, there is a problem that it may stuck into a local minima, may not be the global optimized one, because I am picking one by one. As you can easily see, if the second one converges better with the second one and the best in the third, then that combination is never reached by me. I hope you can get it. If the second best during first selection, second best during second selection, and the best during third selection comes up, then that combination will never be. So I am pruning my search space in terms of some heuristics. That's the overall forward search. Okay, agreed?
So reason
Yes, sir.
plus d minus 1, because in the next time we are just means not considering that attribute, means when we are choosing
Sir.
a.
You are correct. I mean, it's you can say order of this. You are
And
correct.
I have another question, sir. How it is means order of d to the power d? Isn't it 2 to the power d?
I mean, order of d to the power d is obviously 2 to the power d as well, because d is a constant. Because you expand this formula, it is d into d minus 1 into d minus 2 up to d minus small d plus 1 divided by, divided by d factorial, the combinatorial formula. It's an exponential.
Okay.
It's a combinatorial formula. Obviously, it is more than this. That's what my point is. And it's huge. So can you guess what do I mean by backward search now? I hope you can guess by now. What does this mean?
At first select small.
Yes, at first we shall take all the attributes and then
Correct.
we shall use one by one.
Yes.
Yes.
First take all the attributes. First, if I remove x1, what will be my KL divergence? I will compute. If I remove x2, keep x1 and only remove x2, what will be my KL divergence? So after one iteration, I converge to a set of attributes with capital D minus one number of them, the best one, then capital D minus 2. In this way, I move up to capital D minus D number of iterations in the same manner. So both you can see is a quadratic rather than going for an exponential one. I'm not detailing out this because you got the idea, I think. So this is called feature selection because we are selecting a feature. Remember, this is feature selection. However, and it's also called a sequential forward search and sequential backward search. I forgot to name it as sequential because it's sequentially, we are going in a sequence. However, if you see, if I again try to draw this points in a different order, let's say I have these points. Now, if this is x1 and this is x2, now if you project here, vis-a-vis, if you project here, you see that these are your two classes here, and obviously these are your two classes here. Now, in such a scenario, how can you choose an attribute? Because both are good separable and you only know these points, you cannot generalize beyond the unknown points and all. So there, I decided to figure out that how do I select the best set of attributes, or how do I extract the best set of attributes. So this is a question that we call it sometime as a feature extraction. If you can see that, obviously, if I could extract this in terms of this axis, that means I could project all of them in this axis. The difference or the separability is obviously more than I have in any one or a pair selection. Agreed?
Yes, sir.
That means, though I am not reducing the dimensionality only by looking at the subset of attributes, rather I am trying to project, here in this case it's a line, but I am only looking projection of point with respect to this line. Remember, this is also dimensionality reduction because this is only one dimension where I am projecting, right? However, it's not only x1 or x2. That means this x1 and x2 projection is a special case of this, where alpha 1 equal to 1 and alpha 2 equal to 0 gives you a projection in S1. So in more clear words, or in diagrammatically, what I am trying to do, suppose I have a point here, and you know that this point is x1 comma x2. This is x1 comma x2 point. I have a line here. This is alpha 1 x1 plus alpha 2 x2 equal to 0, which means any point here is obviously has a alpha 1 times x1 vector and alpha 2 times x2 vector, and along with this direction, that vector is alpha 1 x1 plus alpha 2 x2, which means the projection of this point here would result into this position. That means if I put x1 x2 here, the alpha 1 x1 and alpha 2 x2 value that I get, this, if I try to project here as per the projection rule, that is the norm divided by root over alpha 1 square plus alpha 2 square is the perpendicular distance, and this point perpendicularly project to this line. So this is, we call this as feature extraction, because not we are selecting a set of attributes, but in general we are trying to figure out a hyperline rather in a multi-dimensional plane. Now you may also argue that what if I, instead of only one feature to extract, I want m number of features to extract. No problem. If you want m number of features to extract, that means, for example, I have a 3D plane. Suppose I have a 3D plane x1, x2, and x3. This is x1, this is x2, and this is x3. I want to put it in only this kind type of a plane somewhere, which has some angle with all of them. So no problem. You know that how to construct a plane from a 3 dimension. Since I can construct any line y equal to mx plus c from anywhere and then project the point, then you know that how to do it in terms of this. So there, if it is a line, then I extract only one attribute out of the attribute set. If it is a plane, I extract 2 attributes out of the attribute set. But this whole thing is called extraction. Now, the only thing that we did not formally state it here is that which line. I mean, this line, this line, this line, which line should I project? Again, the normal intuition will come into picture here. Let's say I have a set of points like this.
Sir,
Yes.
so how are we selecting one dimension, like by drawing the line? How are we selecting among x1 and x2, like which one will take as
No, I said that you can choose any alpha 1 and alpha 2 and can get any line. I want to project it in a line rather than in any one of the axes, because one of the axes is a special case of this general case, right?
Okay.
The projection is not over axis, projection over any arbitrary line that I choose on, but still it's dimensionality reduction, right? Because I reduce into only one dimension. Now the second question, as I told you, whether this line or this line or this line or this line, which I will choose. So for that, you can easily see that it forms the data cluster that it forms. If I have to choose one dimension, I will try to choose a particular line which is in the principal axis direction of it, right? That will give me the better divergence, to so as to say, or distribution of the data if I project it there. So it is basically the principal, it's not principal, it's principal. The principal axis of the distributed data points I need to find out. So this has governed to the algorithm of feature expression, which is called as principal component analysis. And it's purely based on statistical features, which you can easily understand the intuition if I give. So what I do first, for all the points, step number 1, I compute the mean for all of the points. So this is x1 and this is x2. There could be many dimensions. So for all of these points, I will compute x1 dash equal to whatever the value of x1 is given to me. Suppose this point has x1 comma x2 value. So each of the point, I just compute mean of all points, and the point I just minus it. So x2 minus mean of all points. So this is mean of all training examples that we are given. So what does this transformation will do if I do it for all the points? Let us draw the same figure. Your data distribution will now look like this, right? Because the mean somewhere is here. If you extract from every point, it will be, your mean will come to center and this will shift. Agreed?
Yes, sir.
So you were taking the mean corresponding to one dimension, right? Like x, y,
Yes.
x1.
Yes. Yeah. So that means if this will be minus with the mean, then this point that you can see will be somewhere here. Right? That point could be somewhere here. This point, if you take all the side mean, that could be somewhere here. So it means I just align them across my center border. Okay. Step number 2. So from here, what I do, I try to produce a covariance matrix of all the points in capital D dimensions that I have in my hand. So that means covariance of x1 with x2, x1 with x3, similarly x2 with x3, and so on. And that matrix, as you can easily see, it's a D-dimensional covariance matrix. So it's a D cross D covariance matrix I will get. That is step number 2 from here. After I transform the means, points reduced by means and spread it out over the center. Step number 3, what I do is that with this covariance matrix, I will try to find out principal eigenvector. That means, you know that how do I get the eigenvalues? If you solve for lambda, you will get all lambdas. That is your eigenvalues. Now, if you take the highest eigenvalue, that will correspond, the vector that corresponds to the highest eigenvalue will be your principal axis. The vector that will be the next highest will be the secondary axis, and so on. So now you can see easily, if I want to get d-dimensional space to transform these points, I will take highest d lambdas and correspondingly eigenvectors of that, and those eigenvectors corresponding to highest d number of lambdas will correspond to all the d principal axes, one after another. Top key eigenvalue take, calculate the corresponding eigenvectors using this formula, and you get whatever be your principal axes. Now, with that vector, see, a single line is also a vector of alpha 1 and alpha 2. It's a two-dimensional vector because we are projecting a line in a two-dimension. It's a d-dimensional vector. If you have a space like that, your eigenvector will be d-dimensional. Obviously, it will be d-dimensional. It is d cross 1 eigenvector. So each of them will look like this. Now there, you can project your points and try to make the class separability. So this principal component will give you the best class separation. Okay, so this is what is the buzzword about principal component analysis. You transform the point across center, try to find out the principal axis, that is the most dominant axis where the divergence is more. Top D among them are the top D at dimensions where you can get this. Calculate the eigenvectors or the hyperplanes for that, and then those are your projection areas where you will project and get the best KL divergence. So this is called feature extraction because this term comes from the fact that you extract a feature. It's not just given to you as an attribute and you select. Okay.
Sir, what is the intuition behind taking highest lambda?
Yeah, it's the intuition is that to take the principal axis. Intuition is to take the principal axis. The highest lambda, the eigenvector corresponding to highest lambda in statistical parlance, if you take that will be your principal axis. That is the axis where the distribution is highest. The second highest is the second axis where the distributions will be second highest, and so on. So you want to choose such kind of D axes so that you get best class separability. So those axes should elongate your data in terms of distribution. That's the intuition.
Okay.
So however, I just end up this with this very small kind of a exploratory puzzle that suppose you have points, two separable classes like this. Now you can easily see that if you try to draw your ellipse, obviously your principal axis will look like this side. But if this be your final principal axis where you will project, then this is not a separable one. So obviously this method has certain question marks now over it. Agreed with the drawback?
Yes.
So then what people have thought, I just give it to you because it is in the slide, the formal equations, the formula is they try to compute the centroid. And it's called Jacob linearity discriminant analysis. Suppose these centroids are M1 and M2. Then what they try to do for each of the points, not only they try to figure out whether this axis will give them class separability, but also if I project the centroid, how far they are. So you can see if I project it here, the centroids are not very far. Rather, if I project the centroid here, they are very far. So this, though principal component analysis will result you the principal component axis of the whole distribution, but that is not always an indicator, and therefore they try to sometimes use such kind of a index, some index to distribute the point so that your principal axis becomes well aligned, not whatever just the principal component returns. So these are some of the ramifications of this approach. There are many ramifications could be possible and according to the anomalies, but the concepts that we would wish to make here is that you need to select a set of feature is number one. And now in this slide, what we have shown is that you need to extract a feature through which your separability would be maximized. And for that, you could also invoke certain different kind of paradigms as well, as we have just shown from a ramification.
So that will work for only 2 clusters. What if we have the 3 or 4 clusters? Then how will you find out?
No, then there will be pairwise mutual discriminant analysis, and depending on the pairwise mutual discriminant, they have a metric for that.
Okay.
They will pairwise compute that which will be the better one, which axis will pairwise give you best separability. See, separability with respect to pairwise is obviously needed because if you have multiple classes, then there should be pairwise separable,
Okay,
right?
sir.
Yeah. So they will just compute through pairwise every cluster. So this is what I would like to mention about the dimensionality reduction, which is due to the making it computationally efficient. Purposefully, I also want to show you about the other part of it, which is the kernel methods. So if you remember what we did in kernel methods, that I have a x dimensional point set of points in a particular set of attribute space. So this is x1 up to xt attribute space. I make a transformation and put it into a z dimension, which is obviously more than these dimensions. Why I need to do that? If you think carefully, that there is a situation where I need to classify between points which are like this. So no linear separable classifications can happen. Then what I did, I make a transformation of those points, and that transformation resulted me kind of a linear separation, because what I did is that I kind of transform it. It looks like the separable thing is this non-linear. So I transform the point as x squares. And when I transform that, I found out the point spread like this, right? You remember, right? This example we have covered, and we could get a linear separability. And then finally, upon getting that, we transform back again to the phi inverse to get the original line here. So since this is much more efficient to get, we often has to go into higher dimensions as well, provided that the dimensionality does not ruin your sport. But in today's lecture, we will try to see something called a kernel trick, which even I do not want to visit to this dimension, but I can compute and come back. So let us see. Not always the dimensionality increase will ruin your game. So if you remember the support vector machine, since we did the support vector machine to minimize our loss with respect to alpha, where the formula is summation over all the points minus half summation over all the points, summation over all the points, ym alpha n alpha m zn transpose zm. Now in the support vector machine, this is what we compute from Hessian matrix, right? And this could be, if it's a linear kernel, this could be xi dot xj, which is being put in the Hessian matrix. If it is a linear kernel, remember, right? Everybody,
Yes,
you
sir.
remember this, right? So we have a matrix called Hessian matrix where we put up all these y1, yn, ym, xn dot xn. So dot product, I just written it as transpose into multiplication, is just the dot product, nothing else. So now you see that depending on the values of the dot products, if it is not a linear but a different kernel. So suppose my kernel is a very simple polynomial kernel. So what if my Z transpose Z is nothing but a kernel of Z transpose Z bar is nothing but a kernel of these 2 points, which let's say that Z is phi of x, and I just transform it like this in a square form. So I have the attributes like x1, x2, x1 square, x2 square, x1, x2. This is a complete transformation of Z from the point x1, where x is a 2 attribute point, right? I can make such kind of a transformation. So then my kernel that I would like to make here is obviously this transformation set will be twice done. So it is obviously 1 plus x1, x1 dash plus x2, x2 dash. It's a dot product, right? Between z1, between z transpose with z dash. So dot product between this and this transpose. So if you go by that, now in order to compute this, if I have to visit this space, this particular Z space, in order to compute this, then you see the problem with my hand. I need to compute all of them and then get back to my solution. So rather, the kernel trick suggests you that indeed you do not have to visit to all these dimensions to do it. So rather what you can do, so suppose I give you a polynomial kernel. I will just give you, I will tell you that what is the kernel. I will tell you the kernel. The kernel is a polynomial kernel, and you know that the polynomial kernel follows the equation of let's say degree 2 polynomial. So if you know that, then obviously you can compute this will be x2 dash plus 2 into x1 dash x2 dash. Now see, I do not know whether this kernel will transform me to some space. I do not have any idea of some space. What I only need to know is that if I can compute this, I am done, because I can only substitute this value into Hessian matrix, which will give my support vectors and a line discriminator. Whether it's a valid inner product of x1, x2 transformed into phi x is a question, but you can easily see the polynomial kernel is a valid inner product where I have this as my attributes, because here the 2 is playing the spoil sport, so I can easily round down to these 2 values. So this is one point, and the other point subsequently will be x1 dash square, x2 dash square, root 2 x1 dash, root 2 x2 dash, root 2 x1 dash, x2 dash. So which means that this is my phi of x1, and this is my phi of, sorry, this is my phi of x, and this is my phi of x dash, where x equal to x1 comma x2. So now you see, you only need to know the kernel. You do not need to know phi in order to translate the space, right? Why it is beneficial? Rather than 2, if you go to a qth order dimension, then each and every value of your particular point, each and every attribute value of your particular point, you need to convert every point into this higher dimension space. Suppose it is, instead of square, it's a q, polynomial of order q. Then the computation to convert and come back is huge, rather than I only need the values from it, and if I can expand and do it, these terms will be much lesser to do, rather than I convert each and every point and then try to take a linear product of those 2 points. That's what is so interesting about this kernel trick. Is the philosophy clear? What I am trying to do here?
So the last keyword part, can you please explain
Yeah,
again?
what I'm trying to do, see, when you try to discriminate something in a higher order space, what is your goal? You cannot discriminate in this space, X space.
Yes, sir.
So you need to go to some other space. Now that space, you should have an idea what that space is, because you should have a knowledge of phi. However, what I'm saying is that if you could build a suitable kernel, just note my term suitable, because there is a condition for that. Not everything represents a space. If you could
Yes.
build a kernel which can represent a Z space, I am saying you are not needed to visit that space in order to find your discriminant. Only what you need is there is an existence of such a kernel, because in that case the kernel value I only need here the values of k, x1, x2 here. In terms of this, I only need these values to be supplied, right? So
Yes,
therefore,
sir.
I only need this computation. I do not need each and every point to go into Z space and then compute and come back. If I could design a kernel so that it exists, it projects an existence of a Z space. Agreed?
It is giving us a
Agreed, sir. Agreed.
Yeah. Somebody's question. Given that,
so sir, it is giving us a kind of linear transformation to that space. Directly confirming this. We are trying to compute the linear transformation to go over there.
yeah, but the beauty of this is that, see, I do not care about what the G space is. I do not know even what the G space is. I will say, you give me the points, I will translate it into some higher dimension space, and I will show you that higher dimension could be infinite. I mean, it doesn't make sense at all, the space, but I would rather can build a kernel in such a way that in that very high dimensional space, I could segregate the points and then come back here and can present you the solution. Okay, I mean, does it make sense to your question?
So, yes.
Okay, so now see, we are looking at the polynomial kernels, which is of the order of x1, this to the power q. However, we can, so these are finite dimensional space, though higher dimension, but finite dimension. However, we can absolutely visit to an infinite dimension. We do not have to bother where we are visiting. Look at this kernel. Suppose I give you a kernel like this. So my kernel is e to the power minus some constant gamma x minus x dash square. First of all, it is infinite dimensional. How? Let us see. So we will expand it using Taylor series, which means this is e to the power minus x square, e to the power minus x dash square, summation k equal to 0 to infinity 2 to the power k, x to the power k, x dash to the power k divided by k factorial, because this is basically e to the power 2x into x dash. This is a square term, so somewhere 2x into x dash will come. So x square plus this x square, all minuses comes due to the initial minus, and this is 2x x dash. I put it in norm because it's just a matrix, and I need to take a square of the two matrix, right? So that's why I need to put a norm. It is nothing but this. Now look at that this is infinite dimension. You can easily understand what is the inner product of this. If I could find out one inner product side, you can do by looking at this, and the other inner product we can do by looking at this and this. Only spoil sport is the this part. So what I will do for this part, I will make a root 2, the root of all these things, and can divide it among these two classes. Therefore, my inner product could be this is one part. The other part of the inner product, as I mentioned, is e to the power minus x dash square see, these are constant. I can put it in any way. So just to make sure that, see here, what we are doing, that to this is the overall kernel. That means inner product of some 2 points which are in G space. The inner product of those 2 points individually look like this. Here it's a kernel which has infinite dimensional space because this each of them is infinite. So if you write the terms, the number of terms, the phi value in Z space for each of them is infinite number of terms, right? So now see the beauty
Yes,
of
sir.
you can compute this value. So what you will do finally is think about your Hessian matrix. You will just instead of x1 dot xi dot xj, you will just compute this value, kernel value, and keep it in your Hessian matrix. So your Hessian matrix earlier computed y1, y2, x1 dot x2. Similarly, y2, sorry, y1, y1, x1 dot x1, y2, y1, x1 dot x2 dot x1, y3, y1, x3 dot x1. This every other terms you can also think. If you can think of y1, yk, x1 dot xk, so on, y2, yk, x2 dot xk, and so on. Now, what I am making a transformation here, I am putting it into Z space. I do not know even what the G space is like here. It's an infinite dimensional G space. I can never think of. But what change I need to make? I need to compute this. So the Hessian matrix just changes to y1, y1, kernel of x1, x1. Right? y2, y1, kernel of x2, x1. So on, everywhere. So what essentially this rings us is that everything is same. Kernel, you do not need to go into this space. Earlier, when I was trying to classify these points, I was performing to visualize the G space in such a way that it looks like this with the transformation. I need to see the G space from X space. Here, I am totally saying that your G space is opaque. You do not need to think about the G space. All you have is that this kernel that will give you the values of the points in G space. Depending on that, you go on, make your support vector separation and all that. Okay, agreed? This is a nice trick.
Yes, sir.
Now, the only concern that may bother you is what about VC dimension? You are going to infinite space, so you're gone. But see, the mostly we use such kind of a concepts to get a support vector. So when we get a support vector in certain infinite dimension space and we get a support vector, then essentially this thing though I didn't cover about the in the theory that E out is obviously bounded by the number of the E out or the expectation of the E out, the expectation of the number of support vectors you have divided by the total number of points. So as you can see, the only thing matters here is that how many support vectors you get it. I may go into infinite dimensional space so as to not visualize, but to realize a discriminant very well, but come back with 9 support vectors. I am in a very good position, right? Because the expected value of E out, sorry, the expected value of E out here is the expected value. It depends on the number of support vectors that you could support it. Though it's a debatable about this proof because I have not proven it, but believe me, what we are trying, the only part that is governing this kind of kernel trick is the fact that when you transfer into higher dimensional space, you are thinking that your generalization boundary is getting too much bad. It is indeed not, because sometimes the discriminant is only with respect to support vectors, and generalization bound with respect to less number of support vectors makes your dimension to be very restricted. But it's a very nice trick because now we are in a situation that we could visit anywhere and knock the door and come back with the result, replace it, we get a new separator in there. And indeed, this is called radial basis function. And as you can see, this is a Gaussian function, kind of a Gaussian function, or rather an exponential function, where the distance between the term has a negative impact on how the dot products or the relation product will be taken. So that's why it's totally a new dimensional thing, which is a radial basis function, which we will cover in next class in very details, and I will show you the ramifications of taking such kind of a kernel functions in every possible classification or clustering problem. So radial basis function is a very universal function which can be used as a model, even as a model for classification, for clustering, for support vector machine, everything, for regularization as well.
So this expectation formula giving us the bound to our support vector machines, right?
Yes.
Then how are we going to choose?
No, see, the whole gamut here is that if you, so when you translate a point into a higher dimensional space, obviously you are trying to find a separator or discriminant in the higher dimension. Then your generalization boundary will obviously shift a little bit vague.
Yes.
Agreed. Now the question is that here we are talking about infinite dimension translation. So your generalization boundary doesn't make a sense at all.
Yes, sir.
But with respect to the support vectors, you see my discriminant, if I only know the support vectors, I do not need to know any other points to make the discriminant going. Right?
Yes, sir.
Now in VC dimensions, you do not care about the number of points that is there in the distribution. You only care what are the number of points given to you. Right? Depending on that, you find dichotomies and all that.
Yeah.
Not the infinite space. This rings a bell because now my support vectors are the dictator points of my generalization. If I get 50 support vectors, I have a tough luck. If I get a 9 support vector, I am very well in generalization. Because the support vectors will give me new dichotomies to say.
Yeah. Yes, sir.
That's the overall goal. I do not formally prove it because all these things, see, I mean, the relation where this intuition, as I said, your intuition will be backed up by statistics. We will go some towards that, but I cannot cover all because it's a full-fledged course of advanced machine learning and statistical machine learning, which is there in your other semester. So the intuitions that we will try to project here, though we move by kernel trick to infinite dimension, but generalization, we are not sacrificing that much. Because we only need a set of points to classify or to make a supporter. Okay, so with that, I end this. As I pointed these two concepts because it looks conflicting, but there are two things. I mean, two different aspects to it where it can be applied. Dimensionality reduction has one particular thought process going where to be applied, when to be applied, and also this kernel trick has another ramifications to think of. So with that, the major thing that I will carry forward is this function that is a radial basis function. You can see I can use this function not as a kernel, but also any model to just learn and classify. I can use this functions for k-means clustering. I can use this function for k-nearest neighbor. I can use this function for support vector machine because this function is nothing but it has a nice relation that the nearing points, the more nearer the points, the less the penalty. The more further the points, I do not care at all. Right? If you look at only this function expression, e to the power minus gamma of this. Right? If x and x dash is too much separated, then it goes down. The value goes down. So I do not care, just like. So doesn't you give you a kind of a thought process that it can be used for clustering? Right? It can be used for clustering. It can be used for k nearest neighbors. So we will see all that. Any questions?
Sir, I have one question for a little bit clarification. That in the first two board, we are looking for some type of clustering where we can able to separate the cluster with a perpendicular perpendicular line in either axis. And
In
for
either
the
axis or maybe a feature we extract anywhere.
anywhere. But for the next part from board 3 or 4 where the kernel concept is coming, is there any concept like this?
No.
Cluster is not separatable. That's why we are going to
Yeah, absolutely,
use some
absolutely. You
plane.
cannot separate it with the machinery that you have.
Yes.
So we need to go to higher dimensions to make it look separable much easier way.
And therefore we are just try to build two separate planes and then just make the hyperplanes and then make the total mirror
and
image
then
or
come
something
back,
else on that
and
plane.
then come back with the just the clusters with just the kernel. Go there, calculate, come back. Do not know where you are going.
Acha, go there, calculate the space and then come back. Okay.
Come back. You do not know where you are going. You have a function to compute. That's it. Now, the only thing, how do you choose these functions that I missed? The only thing that you need to bother here is that this matrix, the Hessian matrix or the function matrix that you compute should be symmetric. That means the matrix of kernel with not the y1, y2s there. Only the matrix of kernel.
Matrix of kernel.
Kernel should be symmetric and semi-definite. So
Semi-definite.
I already when I mentioned in support vector machine where what is the property of this kernel, I mentioned these two. So it should be, so these are called Merker's condition. A scientist called Merker first found out these conditions. So the kernel matrix should be semi-definite and it should be symmetric. This is the matrix of kernel.
Okay.
So then only if so what now the good thing is that you only need to calculate such kind of a matrix which is symmetric and semi-definite. You do not even have to look into G space. Where you will go, you do not know. You know that I have a matrix according to Marcus condition that will give me decompositions of these two sector points, which individual is a Z dimensional attribute space.
Yes. That's why if the phi is infinity, then it's not matter, na?
It doesn't matter because if in support vector it absolutely doesn't matter because it only matters with the support vectors. Okay, that's why people use it mostly the infinite dimensional kernels, and which has a name. It is called a radial basis function. It is very much used. So in machine learning, we say something you have to know that AdaBoost you should know. Okay, and this is one of them that you should know. If you have done a machine learning code, you should know what a radial basis function is. You should know what AdaBoost is, because those are the two inventions in machine learning which makes this field. I mean, a very much, and the third is obviously the neural network where everything comes. Okay, so that's it for today's class. If you do not have any quick questions, we can stop. And next day tomorrow I will do the radial basis one in detail. Any quick questions? Okay.